3 years ago, man.
Yeah, indeed, and we were on.
Yeah.
And you're Arun Kishan.
Yeah.
And you're an architect now.
Yeah.
The last time we talked about process management.
Yeah, we did.
And so you've done something really incredibly interesting in Windows 7 around a dispatcher spin lock.
Yeah.
Can you talk a little bit about first principles, kind of get people up to speed with spin lock is kind of an old term from Unix days.
Right. Okay, so we basically, I'm going to just go on
Absolutely.
whiteboard. All right. So we have basically two types of locks in our system. You'd have a passive level lock, and something like this basically implies that if the thread can't get the lock, it'll block.
Okay.
And so all user mode locks fall into this category, right? Typically if you can't get it, you'll block, and the schedule will pick another thread. In kernel, there's also a set of locks. We have like push locks, like fast mutex and things like this are passive level locks also. It's a little bit of a misnomer because in kernel you could have up to IRQL equal to APC level. We'll talk about that in a second. But basically, the idea here is that you can block, whereas with a spin lock, the idea is typically the hold time's pretty short, so you'll just spin waiting for the lock. And in the kernel, this raises to dispatch level or above, which basically blocks the thread scheduler. It's an interrupt request level, and you say, okay, once I get this lock, until I release it, I'm at dispatch level, and also someone who collides on the lock and spins waiting for it will also stay at dispatch level and they won't be preempted. So what this means is you would expect it to be acquired in pretty short order. In user mode, you could implement a spin lock as well, but it's not a true spin lock in the same sense because the OS could preempt you. You could take a quantum end or whatever in user mode. And so a lot of the core kernel structures are protected with spin locks because the environment and the hold times associated with them. We tend to use these spin locks, and there have been a couple over time that have been pretty frequently used in most workloads. One was this dispatcher lock that you've heard about. Another one was the memory management PFN lock, page frame database lock, and then some locks in the cache manager.
All right.
And so these three locks tend to show up quite a bit on a lot of the server class workloads we see. And when I say show up, what I mean is that the contention on the locks tends to increase the more processors you add into the mix.
Okay.
Right? And so when you only have one processor, it's not a big deal. When you have two, they'll collide once in a while. When you have N, where N becomes large, and in Windows 7 now we're supporting greater than 64, so we're up to 256.
Nice.
You could expect that, if any lock has a particular given hold time, that hold time now reflects a window during which the other processors can collide and spin. In the case of spin locks, or here they'll block, but threads will block. But for spin locks like these, the processors just spin, and the time that they spin waiting for it is basically wasted CPU time. And we have two classes of spin locks. One is a unfair spin lock. The idea here is it's kind of not it doesn't maintain any ordering. So if two CPUs collide and the lock gets released, the first guy who collided isn't guaranteed to get it, right? It's just whoever sees the traffic available, or whoever sees the memory available first gets it. So this has some advantages where there's less code to acquire and spin on a spin lock, unfair spin lock, but it's pretty noisy as far as cache goes, right? Because as soon as you release the lock, all CPUs see it, and they'll all try to acquire it again, and they'll all ping the line around. And so it kind of degrades under very high contention.
Okay.
Then we have what these are fair spin locks, also queued spin locks. And these guys actually maintain an order. So if the lock's held and CPU 0 comes in, he would go on the head of the queue and then CPU 1 and so on to CPU N, right? And so when the lock gets released, it's actually passed directly onto the first guy who arrived. And so you actually have a guarantee between when you start waiting and when you'll actually get the lock. At most you'll have to wait for N-1 CPUs. The problem here though is that you basically pass the ownership, right, to the next guy in line. And so this tends to degrade under like virtualized scenarios because the hypervisor may not be running this CPU at the moment. So you're familiar with virtualization?
Yes.
Yeah, so the hypervisor runs each of these on the real processors, but they're context switched. The CPUs actually become like threads as far as the hypervisor is concerned, and it could be running some other CPU. So if this CPU is running here, and it's spinning, it could actually get expanded by the amount of time it takes the hypervisor to switch in all the guys before it, which is not necessarily true on real hardware, but it becomes true when you use queued spin locks in a virtualized environment.
Okay.
So we're kind of in this interesting place with that where historically, whenever we've had very high contention locks, we've switched to these fair spin locks to make sure A, everyone gets a chance at it, and B, they don't have this cache pinging because when you queue yourself on this list, you spin on local memory. You don't actually spin on the memory address directly, and so when I pass ownership, I just clear your memory, your stack local, basically memory address. So it only wakes you up. It doesn't generate a whole bunch of cache traffic. But as we see, that behaves poorly under virtualization. And the second part of that is that when there is no contention, there's like more code involved here than the simple set a memory address, spin on the memory address. With a fair spin lock, you basically have the extra setup of queuing a block on this list and then releasing it, popping that off. And if there's no contention, that's all overhead.
Okay.
Right? And so we would like actually to go to a model where everything is unfair or closer to the unfair model, but we don't have contention on it, right? Because when you don't have contention on it, there's no real cost. Yes, there's a little bit of unfairness, but if the hold times are very short, ideally everyone can get through it.
Excellent.
And so out of these locks, the hottest of them all was this dispatcher lock. And so we'll talk a little bit about what that guy's about. So the dispatcher lock is basically this global spin lock we had in the kernel that effectively protects all the anything related to threads. So this is actually the thread dispatcher. So that's where this comes from. It's the scheduler lock.
Cutler world.
Yeah, yes. And a lot of work had been done over time to like break this thing apart, but fundamentally it's kind of tied into the state transition of a thread from running to waiting. And this is usually done in conjunction with examining a bunch of objects. Call them wait objects. Right? So basically the idea is your thread's running, you want to atomically examine some set of objects and then go into a wait state, right? And so all kinds of code that might intersect with this behavior also have to take the dispatcher lock. And you'll see that pretty rapidly that it grows into a whole lot of code in the kernel. So, for example, all these wait for single, wait for multiple objects are two APIs where you can like wait on an object or wait on a set of objects. Those end up requiring the dispatcher lock because all these objects that you specify here are actually synchronized with this single lock, the state of them. And the reason it wasn't done as like per object locks is because I could be waiting on A and B, some other guy could be waiting on A and C, and you kind of want, in both cases, right, all the objects are kind of synchronized by the same primitive. So because of that, it was implemented so that there's just a global lock across all of it. And you could get into situations here where if you're not careful about how you lock, for example, this is A and B, this is C and A, or B and A, sorry, you could easily get into a deadlock there, right?
Okay.
Because the other guy gets them in the other order. And so initially when the design started out, there wasn't a real reason to be much finer grained locks than this, because we didn't run on such large numbers of CPUs. But as we grew in the number of CPUs we're trying to support, we get more and more contention on this stuff. So back to here, you have wait for multiple, wait for single, you know, thread priority, affinity. This stuff also cares about the thread state. Anything that relates to these guys, like set event, you know, signal semaphore, you know, mutant stuff, completion ports, like all the stuff that's related to synchronization and thread activation, all of that stuff kind of relates into this equation about waiting on objects, right, and getting objects to run or waking threads up. And so these are pretty powerful primitives that we have for waiting on stuff, because you can actually, you could say that you want to wait for any or wait for all. And so this is kind of like an or semantic, and this is an and. So here you could say I'm waiting on these 10 things and I want to wait for any of them to be signaled. Or you can say, I want to wait on all these things, and then the OS will ensure for you that you'll only wake up when all of them are signaled. And so you can mix match any type of objects in these. Like you could have timers, events, semaphores. You can just mix anything that the OS considers a waitable object in one call to this. And you can have any overlapping objects in another call, and the OS synchronized it all for you. So it's really nice for an application developer. Back in the day, the reason behind something like wait all, because most people would probably use this, I want A or B or C. You generally don't care about a whole lot of objects, except if you're waiting for maybe a set of processes to exit or a set of threads to exit or something like that. Then you say, okay, wait on all of these guys.
Okay.
The other case that this was really designed initially to solve was if I had like n mutants. And this is way back when all synchronization primitives for user mode or kernel mode were basically backed by one of these guys. These are mutex or mut. You could basically have like 5 of these, and you could basically say, I want to wait for all of them to be acquired. So you don't have to worry about a lock order, right? They're made today, if these were separate locks like A, B, and C, you have to define a strict order. In every place that you acquire the locks, they have to be acquired in that order. Otherwise you get deadlocks, right?
Sure.
The OS handled it for you, because you could say, here's A, B, and C, here's B, C, and A, and here's whatever, C, B, and A, like every permutation, and you just say wait all. I want to acquire all 3 of these. And the OS, because behind the scenes there was one global lock, right, the dispatcher, that protected all these, it would just work for the application developer. And so that was a nice property. However, we later found out that, you know, if I acquire a lock that's not contended, I don't want to actually transition into the kernel to actually acquire that lock most of the time. So we shifted away from a model where the primary synchronization primitive is like a kernel object, but it's actually a user object. So something in your address space, just in user mode. And if it's non-contended, the acquire and release stays in user mode, right? And we found that's much higher performance than always going into the kernel to acquire these anyway. Except once you do this now, the burden of keeping track of lock ordering and stuff went to the app developers. And so some of the original benefits of this primitive kind of went away, but this is kind of the really big reason that we have this global lock that synchronizes a set of objects.
Absolutely.
And so as we got into the, you know, greater than 64p stuff, we were, you know, we're running preliminary numbers on these 128 processor machines, and we're seeing that up to 15% of the CPU time is just spent waiting to acquire the dispatcher lock when you run like a SQL database workload or something. So if you look at 128, 15% is like over 15 CPUs are full time just spinning on the dispatcher lock. So that's like burned CPU time, right?
Yeah.
And people don't want that.
No.
They want to get as much performance out of these big iron machines as they have.
Absolutely.
They can get, right?
Especially SQL.
Yeah.
Right?
And so we decided, okay, we're going to go after this, and we can see how are we actually going to like break this thing down and keep the complexity manageable.
Enter Arun.
Yes. And as I had said before, there was a lot of work that was done over time to remove the dispatcher from certain pads. So
Okay.
it wasn't like this huge, like, there's just one big acquired dispatcher lock in the kernel and leave it at the end of the code in the kernel, right? It had been broken up to some degree. Before we get into that, I just want to like give you kind of a picture of how this would look
Perfect.
in the OS. So this is a PRCB, which is a processor control block, which represents basically a CPU. Each CPU in the OS is represented by one of these data structures. And across this, we can have a wait entry. So what these wait entries are, is they're associated with threads. They're associated with threads that blocked on an object while running on this CPU. So over here you have object A, object B, object C. So each object has a wait block associated with it. Or sorry, this is the object. And this is a list of wait blocks. These things are called wait blocks. And this expresses an interest in the object. And so a thread can be waiting on object A and let's say object B or C, right? But B could be waiting on these two, and this last guy, let's say, is waiting on all three. So all the wait blocks of the thread are kind of chained this way.
Mm-hmm.
And for each object, you can also see who's waiting on all the objects, kind of as a doubly linked list. Make sense?
Yep.
So you kind of have this like matrix, right, where you can kind of get from a thread to the object it's waiting on, and from the objects you can like see the threads that are waiting on it. And this other list is basically for when a thread's been waiting from some sufficiently large amount of time, we want to like go ahead and page out its stack. So
Okay.
typically in kernel mode, we don't page out your stack while you're running. It's non-page memory. But if you're in a user mode wait for some really long time, so you can imagine you have a thread that like waits for ages on some event that's very rarely signaled. We don't want to keep your kernel stack resident the whole time. So what happens is after you wait for sufficiently long, the bound set manager, which is like a part of the kernel, like it runs periodically. It will run through, see if you've been waiting for a really long time, and move your stack into transition state. Right? And so eventually it gets paged out. But we guarantee that it'll be brought back in and made resident again before you can run. But the way we can find these guys is because we can just walk down this list from the processors. Each processor has a list of guys that are waiting on it. Now, if you signal an object, you have two types of signals. Basically, there's a third one, which is mentioned, but it's not used, so I won't go into too much detail on that. There's a notification signal, which is kind of like wake everybody that's waiting here up, right?
Okay.
And leave the signal set. Don't like consume it. So this is like a broadcast kind of thing, where it'll go ahead and walk down this list and wake each guy up, and it won't like consume the count, if that makes sense. Then there's like synchronization events or objects where there's actually like a signal state, a discrete count, and for each guy we satisfy, that count goes down. And when the count reaches 0, we can't wake any more guys up. So this is like your events, semaphores, that kind of stuff falls into this bucket. Here you have notification events, which people I'm sure have used. And like notification timers. Basically things that kind of get signaled and stay high until they're manually reset.
Okay.
Now synchronization ones are essential to build any kind of real synchronization primitive, right? Because you release it, the count goes to 1, the next guy who gets it goes to 0, no one else should get it, right?
Absolutely.
So that's kind of the idea of it in synchronization. Then there's this thing called pulse, which is used basically only with events. And so this is kind of a deprecated functionality because it's really hard to use correctly. And we've all decided that this was probably a bad idea to put in and we've built other primitives that replace this. But the idea with a pulse is that I can apply a signal to this thing at this moment, like a notification type of signal, and wake up everyone who's waiting at this moment in time, and then reset it to 0, like atomically.
So sort of like in the, I can't remember the name of that movie, but they come and they flash that thing at you and you forget about the aliens you just saw.
Yeah, Men in Black.
You got it. So you reset everything back to 0.
Yeah, it's kind of like a pulse, so you just like say, okay, everyone who's there right now, everyone who's there right now, wake them up.
Great.
The problem with that is it's really hard to build the primitive that you probably are thinking you're building with this. Because internal to the scheduler, we actually wake these guys up, remove them from this list, and they can run a piece of code called an APC. We'll get back to this in a second. But so what that means is if I sent an APC to this guy, he actually gets removed from these objects temporarily, runs this APC, and then I could have done a pulse in that window, and this guy misses it.
Got it.
Because he comes back to wait after finishing the APC, this has been reset. So you missed the pulse, right? And so this is a fundamental problem with this primitive in that you can't actually build like a condition variable with it. A condition variable is this thing where you can change the state of something and then wake up everyone who's currently waiting, and then they'll like see the signal and then they can see the state change.
Yeah.
In this case, you'll miss it, right? And there's no real way from user mode to build something that won't miss that signal.
Understood. So that kind of breaks the notion of synchronization.
Yeah.
Right.
So which is why I was saying this mode is not supported.
Has been pulsed.
Yes.
Okay.
And so we've replaced it with this thing in Vista called condition variables.
There we go.
Which actually maintain the list. So for user code, they maintain the list of waiters that's like strung on to the condition variable structure. This is a simplified view. But the idea here is that if you signal the condition variable, even if the thread that was waiting here in the kernel is off running something, his private interest in this has been signaled because the condition variable code sees everyone who's chained on. Right? Even though he's out on the kernel doing something else, when he comes back, this thing is signaled. So it's not like a shared state with everybody else that can be pulsed. He has like a private thing that will never be lost track of. Perfect. So anyway, we recommend people who try to achieve this kind of thing to switch to condition variables. Okay, now back to the story here.
Yeah.
So we have this graph. So things that can break threads out of this graph are these signals.
Yep.
An APC, and an APC can be either a kernel APC or a user APC. Kernel APCs are kind of like Unix signals. Unless they're masked explicitly, they can basically run at any time. So when you're in a wait, they can break you out of the wait to run. Or if you're just running in the kernel, you'll get interrupted and it will like run like on top of your thread. So basically what it is a little piece of code that needs to run in the context of your thread or process.
Okay.
Now, when NT was designed, they felt that model is like really hard for user mode code to deal with because you could get all kinds of weird re-entrancy on top of yourself. Like I could be running a little piece of code, I could take an APC, that APC could call back into the same piece of code, and now it's like in this weird indeterminate state because I could have been in the middle of doing something in here and now I'm running on top of that same code in user mode. And for most user developers, that's a complicated thing to deal with.
Certainly.
In the kernel, you can deal with this because we basically have IRQLs, which are interrupt request levels, so you can raise to APC level and mask these things. Or you can enter a critical region or a guarded region. So we can have a whole separate thing on APCs and stuff. But the basic idea is in kernel you can deal with this by masking these. In user mode, you basically never get them unless you say I'm ready for them. And when you wait, you can say you're in a user mode, wait, that's alertable. That tells the OS that if someone sends you a user APC while you're waiting, you're okay with breaking out of that wait, returning to user mode and running an APC. But that's the only time you can ever get a user APC. But the point being, that's one other way you can get out of this stuff.
Okay.
The other thing is an alert and a timeout. Timeout's pretty self-explanatory. It's like whenever you do a wait, you can give a time constraint on that thing, where if it's not satisfied by that time, you'll wake up anyway. The way we implement that in the kernel is kind of neat. Whenever you wait on a bunch of stuff, we just add one more object to it, which is a timer that's set for your timeout value. So this could be like you have an and or semantic on this, like wait any, wait all on the set that you waited on. And then we just add one more thing to it that says it's a wait any. So it's this stuff or this, or A, B, or C, or this thing. And this can break you out. And each thread structure has a private timer that it can add to any wait like this. So that's kind of neat, and then we just leverage the same infrastructure to do this. So that's how a timeout breaks you out. An alert is like an APC, like you have to be in an alertable wait to get it. It's just kind of a lightweight poke. You can poke a guy, you can alert him, and he wakes up, but there's no payload associated with it. So you got to go back yourself and kind of figure out why you might have been woken up, right? What the alert meant. So there you have the full way that you can get out of one of these things. And all of these different ways of waking up and these object signals, you see, have to synchronize. There has to be a well-defined lock ordering here, right, between everything. And APCs, like, they need to know if you're running or waiting. Alerts need to know if you're running or waiting, right? And so the way all this code would synchronize with each other, because there's so many different objects involved, the most simple design was to say, let's just have a dispatcher lock. And then, yeah, we can maybe special case some paths. So in Win2K3, if you take an event and say, no swapping. So swapping is this stuff, right, where you get put on this list, and balance set manager can remove your stack. That poses a little extra complication, because when you're about to run again, you need to bring your stack back. If all of the stacks in a process go out, the process goes out, gets paged out also. And the process being in and out of memory is basically tied to also attaches. So other threads in the kernel that temporarily attach to your address space can basically boost your residency count. So that attach and detach thing relates to APCs, because when you send an APC to a thread, you need to know which process it's in. And so attaching, detaching uses dispatcher because of the APC relation, which means the swapping stuff ended up depending on the dispatcher indirectly, because the residency count of a process used dispatcher. So if you remove that dependency, you remove the ability to have timeouts or multiple object waits, basically. So this is a really simple event, right? You can't like combine it with anything else. We call this thing a gate. And this gate is a special kernel private object that we used in the scenarios where an event was used for these characteristics. And actually, if you think about it, you usually just use an event like this by itself. You have something somebody waits on, you signal it, wake them up. We made that thing a gate in 2K3, Server 2003, and we were able to develop a path through the scheduler that relied only on an object lock for the gate, a thread lock for the thread, and a processor lock, PRCB locks I'll say, to schedule the thread when it comes out of this. Now you can see its simplification because it removes some of these extra axes that we were talking about here that made this problem really complicated.
Yes.
But that's a pretty big bang for the buck though, because a lot of code ends up using this stuff and we could just switch them over to this gate stuff. However, it didn't solve the broader problem, and it doesn't solve the problem for stuff like SQL, because gates are not exposed out to user mode. The one other thing that gates did not handle, that's kind of an additional complication in this whole thing, is completion ports. Are you familiar with these?
Let's go over them.
So the idea with a completion port is it's kind of tied in through the back door to this whole thing. A thread can be associated with this thing, and it has a concurrency count. So the first time a thread removes something from a completion port, it becomes tied to the completion port. And the completion port typically has a concurrency count associated with it that's equal to the num procs in your system. So the idea with a completion port is that it's trying to only keep that concurrency count number of threads running at any time in the system. So if I come and remove from this, and the concurrency count is already pretty high,
Okay.
even if there's stuff in here, so this has packets associated with it. If I come and remove from the completion port and the concurrency count is greater than or equal to num procs, I will be blocked. It won't let me pick up one of these packets and start running. So the idea is to kind of throttle down your CPU usage to be num procs, so you don't overload the CPU, right? So it's pretty nice, but the idea is when you block, so let's say I'm one of these n threads, the concurrency count's n, and I'm one of these guys and I'm running, but I happen to block on some other thing, like an event or page fault or something like that. What happens? Because now I could have some 10 or more threads, waiting on this completion port, and there's packets in here that they could be servicing. So the scheduler, whenever we go into a wait state, if you have a completion port, so we do all this magic,
Yep.
and then we say, does this thread have a completion port associated with it? If it does, we decrement the concurrency count, and if it goes below this number, then we activate. So in this path where we're sleeping the current thread, we actually activate a thread that's related, that's on the associated completion port. So you do all this stuff, and then you have this other object of some interest, which is the completion port tied on the thread, and you can say, oh, actually now the concurrency count's going too low, and if there's stuff in the queue and threads waiting, wake one up. And so on the flip side, whenever you come out of a wait, if you have an associated completion port, you boost this count. And so we don't have the facility today in the OS where if I signal an event and it wakes up a thread and the count is actually already n, that we will stop your thread. We'll just let it run. So this is why you have a temporary oversubscription where it can go over n, but the next time you come around to remove, you'll block. So the paradigm for using completion ports is you have worker threads that kind of just pick up a packet, do something with it, and go back to the completion port. So you never kind of remove and then just keep running. So this temporary oversubscription self-corrects. But, point being, that association from thread to completion port was protected by dispatcher, because wherever you are, you need to get from this thread to this object, and on the other side, there's a bunch of completion port APIs, right, that need to go from completion port to associated threads. Particularly, this is a user object, so I could close the last handle to a completion port, and it deletes the completion port, which means it needs to run through all the threads that are associated with that completion port and remove the association, right? But now you have a A to B ordering and a B to A. So if you had two locks, you have some complexity here, and so why not just make it the same lock, right? And it's the dispatcher. And so dispatcher also fits in through this equation that way. And so the gates, where I was going with that, is the gates that are mostly dispatcher lock free, but if your thread happened to be associated with a completion port, they would also end up taking the dispatcher lock. And so this is kind of the overall view, and I think maybe you get some sensation or feeling as to why.
This won't scale to 256 cores.
Exactly. But also some idea of like why it was done this way.
Absolutely.
Because, there's a lot of things to juggle here, and you don't want to mess any of it up. Right?
Agreed. Well, I mean, and it's also,
it is brain salad surgery that Cutler created, man. I mean, it's not. I mean, that's complex algorithms.
Yeah.
And so, but the problem of the day wasn't the problem of today.
Exactly. I mean, back then, scaling to 256, I mean, a lot of this design works fine for up to like 816. Like, it works great. And then once you start going above 16, then you start seeing this contention build up, right?
Mm-hmm.
And, you know, for 20 years ago, that wasn't, you know, running on 256 processors on a single machine wasn't probably in their wildest fantasies at that time.
Absolutely.
Right? And so basically we have changing assumptions now, and that's why this problem came to the forefront. And now if we look at it, you know, this mostly benefits server today, but tomorrow your desktop's going to have who knows how many, right?
You got 1,000 cores, man.
Right. And so our goal in the OS team here is to like make sure that our core primitives all are like as scalable as possible.
Excellent.
So that, you know, the higher level software doesn't need to engineer around it or worry about using the OS primitives for fear of scalability problems, right? We don't want that. We want to have our stuff be the best and have them worry about their pertinent engineering problems.
Certainly. I mean, and back in the day, when NT was first created, it actually was designed to scale well beyond where they thought things would go, say, in the next 10 years.
Yeah.
So now you're at a new iteration where now you're like, okay, now we're dealing with 256 cores or 256 processors. Then we're going to deal with the world of hundreds of cores per chip, and then we're going to deal with thousands. Then there's all kinds of crazy things that Windows will have to scale to.
Yeah.
And then, of course, with the emergence of cloud computing, I can see how this also relates.
Yeah. I mean, a lot of the principles in building like scalable systems kind of apply to distributed systems and whatever, right?
Of
So,
course.
yeah. So
right on, man. Great job. But now we get to talk about what you did.
Yeah.
Understanding. So it's great that we have that intro.
Yeah.
So now people watching this, take a break, go get a drink of water, get some potato chips, come back, and now learn about what you did to make this work to scale.
Okay. So, in a nutshell, the idea is I made this thing be transactional. So I'll give a little more background on what that means, and then the whole thing kind of falls out from there. So when I looked at it, there was kind of two high-level ways to solve this thing. One, it was to do an object type block. So if we look at it, most of these things that we talked about in the previous diagram all had locks associated with them. But the thing that tied them all together, like kind of the outermost lock in most cases, was the dispatcher.
Okay.
And the most problematic thing to deal with were the objects, because you can have basically any number of objects, and they can all be in a weight multiple. And so they can all intersect in some way. And so the dispatcher removed the complexity of lock ordering there by just saying there's just one lock between all objects. So you could have intersecting sets between different threads, and it just worked out. So there's kind of two solutions you could do to break up the dispatcher's use for protecting objects. One is to do an object type lock, and by this I mean, let's take like a 64-bit quantity, like a word, and say each bit in here represents a type. So completion port, event, semaphore, so on, right? We don't have 64 types, but basically let's say that we assigned a specific bit to each type of object. Then whenever I did a wait for multiple, I could just set a set of bits matching the types that are in my set of objects that I'm waiting on, and then do like basically a compare and swap operation to a new dispatcher lock sort of thing, and just atomically try to acquire all the objects I'm interested in, right? And once I acquire this, all events, all semaphores, whatever, are protected, and there's like a defined lock ordering by the order of the bits in here.
Okay.
Make sense?
It does.
Now, that's nice, it's simple, right? It has like a bounded number of bits that you're interested in at any time. The problem is, though, that a lot of apps tend to use the same type of object. So if I'm using events, I still have now all the contention here, right? Because everyone's going to be wanting to acquire the event bit, right? And so I haven't actually scaled within an object type class. This would be an improvement over the old design, but it wouldn't really achieve the ideal scaling because we're not as partitioned as we would like.
Got it. Doesn't prevent contention for, as you said, widely used types.
Yes.
Right?
Yeah.
But in a system where that wasn't a problem, it would scale wonderfully.
Right, because now
course-
you've segregated the types, but things are, most people use the same type of object
Yeah.
in the process and different processes, and so you'd still have the contention on that bit.
Absolutely. Okay.
So we said, can we do a lock per object? Because that would be basically as good as it could get, right? I mean, that's as fine-grained, as localized as you could imagine. But the issues, of course, the big issues there are lock ordering. Like, how do we make sure that we always acquire them in some well-defined canonical order? And also, how do we make sure that we don't increase path length? So this is kind of an interesting constraint. Whenever you add more locks to things, so the dispatcher, despite all its scale problems, was just one lock, right? If I wanted to wait on 64 things, I had to take one lock. And so on a small machine, like a 4 CPU or less, there's not going to be that much contention on this. So just blazing through paths that acquired, the dispatcher lock to, lock 64 or 30 objects, there's just one interlock operation that you'd have to do. Now, if we're talking about a per object lock, even on these non-contended machines, I have to lock all objects, right? So even though there's no contention on anything, I have to pay like a whole bunch of additional CPU time, right? And so that's kind of this tension where whenever you scale, you add more locks, more instructions, so that on the lower end, you end up taking more time, but on the high end, you get a lot more scale.
Okay.
So it's kind of this tension that we want to balance. And so that was kind of one of our primary design constraints in all this. And we decided to go ahead with this model. But we wanted to optimize for the fact that wait all and wait any are two different uses. We said let's put all the complexity and most of the cost into this wait all case that no one really uses and make this thing as fast as possible. And specifically, we would pay this interlock cost per object if we have to lock it, but we could get away from, ideally, any lock ordering problems here. Whereas here we have to worry about lock order. Mm-hmm. So we can talk about, this adds a lot of cost, trying to define a well-structured lock order, maybe even sorting objects, which is what we ended up doing. We'll talk about that in a second. But you don't want to do that all the time, particularly for this wait any case, which is very common. We're talking about less than 1%, and this is like 99% plus, right?
Sure.
So, standard principle, make this case a lot better.
Excellent. So due to time constraints, let's dig into wait any.
Okay. So, as I was saying, the basic idea here was that we go from running. Say this black box was the wait logic, which is I look at object. If it's signaled, I consume the signal. If it's not, I put my little wait block on it from the previous diagram, and then move on. And then at the end, I come out in waiting state and swap off the CPU. Okay?
Yeah.
The idea, and this transition phase is atomic under dispatcher. Old world. New world, we go from running to a waiting in progress. Right? So this is kind of a split where we broke the wait into two phases. Now when we're in progress, we do basically this wait logic. And at the end, we basically do a try commit. And if that succeeds, we enter waiting committed, which is basically equal to the old waiting. So the idea here, I can go back here now. The idea here is that when you're waiting in progress, code that might want to signal an object knows that you're in this state, and it can basically bypass your wait. What it can do is, it knows you're running, it just changes your state to waiting aborted. What that means is at the end, when you try to commit, you'll be aborted because your wait's already satisfied by somebody else, and you didn't have to hold a lock across this whole thing. And so when you commit, it fails because it's aborted, and you can just back yourself out of this whole wait logic. Now if we dig into the wait logic, when we're in this wait any case, we look at object 1, we lock it. If it's signaled, we consume the signal. And this logic says, okay, am I in progress? If I am, then commit, then satisfy, abort the wait with this object that's signaled. Otherwise, I'm already aborted. So something else that I'm waiting on has been signaled already, so back out. So, but you see, as soon as so this is if it's signaled, else we put a wait block on it. Then we can unlock the object and move on to the next guy. So I never hold the lock for object A and object B at the same time. I just put my block on there, express my interest in that thing, and then unlock it. And I'm in wait in progress. So somebody else who signals at this time knows that I'm in this state, and they can tell me to just back myself out of this. Does that make sense?
Yes.
So it's kind of this transactional semantic, and then you keep doing that for each object, right? And then if I hit one that's signaled, well, I can just lock all these guys one by one and remove, right? Myself in this code. Now, the wait all case is a little more complex because we kind of guaranteed previously that, you know, if you have A, B, C, and D, that you'll atomically get all of them. You either atomically get them all, or you only get one. Or, sorry, you atomically get them all, or you wait till you atomically get them all, right? So you can't like do this thing where I put my thing on this, and I haven't put it on these, right? Because if this gets signaled, I can't consume that, right? Until I've expressed my interest in all of these things. So in this case, what we do is we actually sort all the objects, which all objects in the kernel have a unique linear address, right? So we can just sort based on linear address. And so we get like a well-defined order from them, and then we just lock them all in that order. And so then you can basically execute an equivalent of the old wait logic code, where you're able to basically check all the objects atomically, see if they're all set, and only if they're all set, take the state, right? Because you can't do this partial thing with wait all to maintain the previous semantics. So yes, so this case has this whole sorting the array, locking all of them in order, and holding all the locks across the whole thing. But as I said, this is less than 1% of the code, so the cost here never showed up in any of our measurements. But it works, which is good.
Outstanding, man.
So the other side to this is when you signal an object, right? So this is someone who sets an event, or, you know, timer firing. Like, it has to basically walk from object to all these wait blocks, right?
Yeah.
And wake up the thread that's waiting there. In the old code, if I came here to signal and I saw a wait block, a wait block entering this, being queued to this object was atomic with the thread running. So if I saw this thing here, I knew a thread is waiting, right? And so I can just go ahead and schedule that guy to run. In the new model, it doesn't quite mean that, right? Because I could be in progress. right? I'm still setting up my wait. I'm like in this code. I haven't
Got it.
totally finished it. So the signal logic now is not like a always succeed thing, it's like a try thing. Meaning, I'll come look at the first guy. If he's in progress, then I can satisfy him. I can abort his wait. I just set the flag in him that says it's aborted. And I consume the signal if it's a synchronization object. Or notification, you don't have to, but we'll just consider synchronization for the moment. I just abort it, right? And then he's going to detect that over here and back himself out.
Okay.
The other case is where it's already aborted, meaning somebody, this guy that's referenced by this wait block got signaled by something else, and he just hasn't gotten around to removing himself yet. Remember I said when we see a signal thing, we'll back ourselves out?
Yes.
Meaning we remove our block ourselves. Well, if this guy sees you in this state where you're aborted, that just means that you haven't gotten around to removing your wait block yet. The final case is like your state's some other, which means like you're like out of this code already. You're running again or whatever, right? It's not of interest anymore. So that's basically the semantic about like one shifting this to two phase where this is incrementally done and you try to commit it. And on this side, like having a try sort of semantic where the signaler knows what state you're in on the other side. And so this kind of has this nice additional property, whereas this whole thing was atomic before, right? Where I would go wait and then swap off. And so any signal that came after I started my wait, so that whole block of code where I decide to look at an object, see if it's signaled, put my block on and swap off the CPU was under dispatcher. So as soon as I released that lock, if I got signaled, I would have to go through a full scheduler path to swap me in somewhere. Now, because all that stuff keeps releasing these locks and I'm in progress, you could actually bypass the context switch in all these cases where you might have already, gone through as an atomic step.
Nice.
So it ends up being advantageous to get like better CPU utilization and stuff
That's
like that.
awesome. So I mean, not only is the solution scalable, it's more performant.
Yeah, we actually found that in a lot of cases that we actually took some path length improvements, because in a lot of the old code we had the dispatcher, which was highly contended, and then we have other locks that were held, to try to have some pads where you only have the other lock, but you don't have the dispatcher. But what that meant is in a lot of these places where I now swapped this thing out for the object lock or some other lock, the path length's basically the same, except for this case where you wait on like several objects, where yes, you have this extra interlock cost, but we have some other advantages, right? Like bypassing context switch,
Nice.
and things like this. So that's basically it in a nutshell.
That's awesome. Well, I mean, that's awesome work. I know the sequel team is stoked.
Yeah, we were pretty pleased with the results that we've seen so far from this work.
Absolutely.
So, any other questions you have, or things you'd like me to go over a little bit more, or that
Well,
kind
I
of
think
covers
this
it?
is I think this is good for for an introductory piece into this is great. I just wanted to come over and talk to the guy who was able to do what Cutler wasn't able to do just because he didn't have time.
Yeah.
But he did want to approach this problem.
Yeah.
And I just think it's impressive that that you did this. You and your fellow devs pulled this off. You're being the architect. I just think it's really impressive. So I wanted to get the face behind the new dispatcher model in Windows 7 Server or Windows 7.
Yeah.
Certainly will have a greater impact on server up front.
Yeah.
So to me, it's amazing. And the fact that you did it all in C# is just incredible. I'm playing. Really nice job. So let me ask you one quick question. What was the hardest problem for you in this?
So I think the most complicated parts of this were kind of back to what we were talking about before. When we do all this, you have to have a very well-defined lock ordering inside the kernel now, because we don't have this global. Whenever I have these A to B and B to A type of things, I don't have a global lock in the kernel that I can just take instead of these two to like sort it out. So wherever we had these cases, and we had about 3 of them, where before it just sort of worked out because the dispatcher, timer, completion ports, like we talked about, and mutants.
Yeah.
These all had a two-way relationship. Here was like between the thread, like we talked about.
Yep.
Here it's also with the thread. So a mutant has a thread associated with it, who's the owner. Likewise, a thread has a list of mutants it owns, so you have to get at it both ways. Timers are in a table. That's basically a hash table of due time. So when a timer expires, we go from the table to the timer. And the other side, when we stick a timer in the table, we go from the timer to the table. So you have like this two-way interactions where dispatcher would help you out in the past because you just have the one lock for all these. But now you got to think of, okay, what are some properties of the state transitions that things can be in where I can exploit this to not have to rely on a global lock?
Sure.
Right, so completion ports have property where the association can get broken, but it can't get remade from the context that we had the reverse path that we have to go, meaning it could go from non-null to null, but then it'll never go back from null to anything else. So we could exploit that to do some clever tricks. Likewise, the timer has a very well-defined life cycle, like it's in the table, it's pending expiration, then it's being expired, and then it's not in anything, right? Kind of like multiple states. And so based on that, you can kind of determine what's the right lock to take. I mean, this is a simplification, but that's kind of the basic idea about how you can tackle those problems and then still like not compromise on your overall goal of trying to have the fine-grained locks.
Nice.
So just getting all that stuff to work, and then I think the other big challenge with this project was like, when I started to write the code, it's hard to do it in an incrementally testable fashion, right? Because you can't just sit down, rewrite this thing, run it, and expect to debug, however it will blow up. And it will certainly blow up, right?
Sure.
And the thing is, it's so complex, so intertwined, you got to do it in some incremental units, but it's so intertwined how the dispatcher was in there that I kind of had to break it into multiple steps where in some intermediate steps, just to get a testable milestone, I would actually do a whole bunch of extra work so that I could actually test the current code base, and then the next milestone I'd actually undo maybe half of that stuff, right? Because I don't need it, but I needed it in the previous milestone just to get a testable incremental step, right?
Nice.
And so I kind of had like 7 of those mini milestones where
Wow.
I was able to get like a running OS, and some of the work was throwaway, but in the end it was good because when we finally got it done, we hardly had any issues for a pretty substantial rewrite of the core scheduler.
That's good architecture, man.
Yeah, thanks.
Nice job. I mean, that's actually a great way to develop a new system because essentially you replace what was there.
Yeah.
So you can't just remove what's there and then expect your partial solution to boot Windows, right? You're going to have a non-working Windows.
Yeah. So you do have to do some throwaway work, but the idea there is it's all good because then you're able to vet the previous end steps you did, and rather waiting till the end where it becomes very difficult to debug what went wrong where.
Nice
So
job.
I think that was a very key thing that I did, which was kind of a little, dissatisfying to some degree, right? Because you're doing a whole bunch of throwaway work, but in the end, I think it was key to the success of this project.
Absolutely.
So,
Well, great job, man.
yeah, thanks a lot.
I'm looking forward to see like how this scales in reality. I know you guys have amazing test systems in Building 26. So,
Yeah.
I mean, it's right on, Arun. Great to see you again, man.
Yeah, thanks
for
a lot.
coming on Channel 9.
No problem. Thanks a lot.
Thank you. Great work.